Welcome to another video for Stat 212. In this video, we're going to start getting into the distribution of a sample statistic. And we're going to kind of start this section by just thinking a little bit more about what we expect to happen when we're looking at a sample distribution and just kind of thinking probabilistically about the situation. So first, let's kind of remind ourselves of this cycle. Or I don't know, cycle is really not the right word, but kind of like this diagram that we've seen before, where we kind of categorize the process of probability versus the process of inferential statistics. So probability is when we kind of start from an assumed truth. We start from a particular distribution with certain parameters that we know, and we think probabilistically about what could happen. So before, up until now, we've kind of focused more on the process of probabilistically describing what could happen with maybe an individual event or observation. Now we're going to be thinking a little bit more about this kind of observed data, where we think about this more as a sample now of like multiple observations. So thinking about kind of the likelihood of a particular sample result and the likelihood of getting a particular sample statistic given there's a certain parameter and a certain distribution that we're drawing from. So we can kind of start this segment by thinking about what sample distribution I would expect to see if there is a particular population distribution that I'm drawing from. So as you might remember, the sample distribution is going to represent the measurements collected from our sample, if I just put them on like a histogram or a bar plot or something like that. And a sample is always going to be an incomplete picture of the population. However, as long as our sample is randomly selected or in some way representative of the population of interest, then we know that the sample distribution should approach the population distribution in shape as I collect more and more data. So we can think about this when we think about maybe the process of rolling a die and observing what should happen over time if I keep rolling that die and recording my results. So first, we can kind of think about this informally. If I were to roll a die infinitely many times, what would I expect this population distribution to look like? Well, if this is a fair six-sided die, then I would expect to see the outcomes 1, 2, 3, 4, 5, 6, and I'd expect to see them in approximately equal likelihood here, right? So I'm a human who cannot draw approximately equal or exactly equal rectangles, but I can draw them approximately equal. So this is what I'm going to expect to happen if I roll this die infinitely many times, is I should be seeing all outcomes approximately the same amount of times. But if I'm sampling, right, if I just have a random sample of 100 dice rolls, I'm not going to necessarily expect my sample distribution to look exactly like this, right? I'm not going to get this perfect kind of line shape. Instead, I'm going to get something a little bit bumpier. And so I can kind of see that if I follow this link to GeoGebra, which, oh, you know what? I don't think I can do this while the video is rolling now that I think about it. So that's kind of unfortunate. But if you are following along at home, you're encouraged to open that and see what happens if you roll a single die 100 times. Look at the different distribution shapes that you might see. But I'll kind of give you an example here. A very plausible situation might be something like this. So just kind of like some varying results. Right, so definitely kind of bumpy. I would expect if I rolled 100 times, I'd probably see at least one of everything, probably at least a couple of everything. But I'm definitely going to see more of some things than others. In fact, I've done this working with middle schoolers before. I've helped design a probability unit for middle school. And so one activity we do is we all roll die as many times as we can and try to record the results. And then we talk about why we got what we got, because invariably, we tend to think this should happen. And when we see this, you might think something is wrong. And so I remember a middle schooler was talking about how he thought that I had like rigged the die because it came out like this, and he didn't believe that this was possible, and that's sampling variability. So you probably know this by now that this happens, but this is what happens when we have sampling variability, and so we shouldn't expect our results to look exactly like the distribution that we're drawing from if we only have a limited number of observations. However, the more samples that I take, the more I'm going to see this distribution emerge. So here I have an example. These are my GeoGebra results from rolling 100 dice, and it kind of resembles what I drew before with differences which numbers highest and lowest. And then we can compare that to 1,000 dice rolls, and we can compare that to 10,000 dice rolls. And we can see with each kind of increase, we're getting a more uniform look. We're beginning to kind of approach this population shape where we should be getting about equally likely for each one. So even though these raw numbers obviously can be quite different, the percentages themselves are beginning to even up. I'm getting closer to kind of 16.67% across the board. So that's why those proportions are just kind of really evening out as I draw more and more samples. So big idea, the larger your sample, the more your sample distribution will resemble the population distribution. Okay. Now, this is where it gets a little bit tricky. This next section is kind of a focal point of why we can do inferential statistics. And so we're going to be using these ideas coming up in the next few pages all throughout the course. And this is an easy place to get a little bit confused. So I would encourage you to read this section on your own, to try the things that I kind of encourage you to try along the way as we go, because this is really important stuff here. One big idea of statistics is trying to approximate a parameter with only a sample statistic, right? And so for the same reason that my sample distributions don't exactly match the population distribution, same thing with the sample statistic. If I take a sample, then my sample statistic is not going to exactly match the parameter that it's estimating. But the larger the sample I take, the closer that sample statistic is going to tend to be, the more accurate I would expect it to be. Now, that said, I could have a sample of 50 and match the population parameter exactly, kind of by chance. And then I could have a sample of 500 and I could be off by a little bit. So it's not like a hard and fast rule as much as it's just kind of an expectation that the more data I take, the more likely I am to be close, the more accurate I'm going to expect my sample statistic to be. And going along with this, we can kind of envision the distribution of a sample statistic that I'm looking at. So if I think about all the different samples that I could take, like let's say that I'm sampling people's heights at the university, I know that if I take a sample of 20, I'm going to get a sample mean. But then I could take another sample of 20 and I could get another sample mean, and another sample of 20 with another sample mean. And so there's kind of this collection of possible sample means that I could plausibly get when I sample from this population. And I can think about those possible sample means kind of forming a distribution. That there's this distribution of possible sample means that I'm going to draw from when I'm sampling. And so for that reason, I can kind of envision what happens when I sample and where I should be in relation to the parameter, and how close I could be to the parameter. So we're going to be getting to that pretty soon here. But we're going to kind of start with this idea of there's a distribution of possible sample means that exists when I sample from a population. So if we go back to the dice for a second, we can kind of think about that if I'm sampling 2 dice, which might seem kind of odd, because number one, why am I sampling dice if I already know what the distribution looks like? But because it's something that we understand, it's probably easy to work with. So we know that that the average dice roll, if I roll a die infinitely many times, if I just keep rolling and rolling and rolling, and I take the average of everything I have, the true average dice roll should come out to about 3.5 because I have 1, 2, 3, 4, 5, 6. So over time, if I take a super, super large sample, it should average out to 3.5. Well, I can kind of think about that if I roll 2 dice and take the average of my 2 dice. this kind of represents the distribution of possible sample averages that I could get. Or, I say sample averages, sample means I mean the same thing, by the way. Right, so over here, this is a sample mean of 1. This is a sample mean of 1.5, a sample mean of 2, 2.5, 3, 3.5, 4, 4.5. Okay. And so these are all the different combinations of 2 dice rolls that give me these different averages. And we can kind of already see if I'm rolling 2 dice, I'm more likely to get averages around the middle, around this 3.5 value. And I'm a little bit less likely to get averages kind of far away. Not impossible, but just a little less likely. And that's if my sample size is 2, if I'm just taking 2 dice at a time. But I can continue to see a pattern that goes on here if I keep rolling dice. In other words, if I take larger sample sizes, if I'm taking 3 dice at a time, or 4 dice at a time, or 5 dice at a time, and averaging out those samples, you're going to notice something. That over here I have 2, here I have the means from 4 dice rolls, and over here I have the means from 10 dice rolls. And the larger that sample gets, the more combinations I'm going to see around that parameter of 3.5. The more I'm going to see combinations that kind of average out around 3.5, the less likely I am to get means around the extremes that are kind of farther away, because there's just not as many combinations that give me those lower values, right? So in order to get an average of 1 with 10 dice rolls, I'd have to literally get all 1s, and that's kind of hard to do. And even the same thing with like averaging a 2, right? I'm going to have to get a lot of 1s and 2s and 3s, because if I get if I get some 4s, 5s, and 6s, then I'm going to have to balance that out with even more 1s and 2s. So there's just not as many combinations that give me these averages around the edge, but there's so many combinations that give me averages around 3, 4, and 5. So the more I increase the sample size, the higher the likelihood that I'm going to see a sample mean around the parameter, and the less likely I am to see a parameter, a sample statistic farther and farther away. So this trend continues as I take larger samples. So the distribution of possible sample means I could get when n is large is going to cluster more and more around mu, and it's going to cluster more accurately. So this is a really, really important idea. The larger your sample, the more the distribution of possible sample statistics is going to converge towards the true parameter it's estimating. Again, for the same reason that a sample distribution kind of mirrors the population as I increase the sample size, the more the sample statistic is going to estimate the parameter, is going to kind of close in on the parameter that it's intending to estimate. So keep both of those ideas in mind. Now, we focused here on the sample mean. That's a really common sample statistic to work with. We could kind of do the same thought experiment with different sample statistics as well, like the sample minimum. I think this is kind of a fun thought experiment. If I continue on this context of dice rolls, there exists kind of a true minimum in this distribution of dice rolls, right? So if my options are 1, 2, 3, 4, 5, and 6, well, the true minimum in this distribution is 1. So then if I think about taking a sample minimum, if I have a sample of dice rolls and then I take the minimum dice roll in my sample, what am I going to get and how often am I going to get it? So if I think about if I'm rolling just like, again, 2 dice rolls, so I roll 2 dice and I take the minimum of the 2. I might get 1, but I might not, right? Because I could get, I could get obviously a 1 and a 1, and that's going to be a minimum of 1. I could take a 1 and a 2. I could take a 1 and a 3. So I can kind of continue this. This is a good place for you to kind of pause the video and kind of finish filling this out. What are the different combinations of dice that I'm going to see? What sample minimums do they provide? And what does this distribution of possible sample minimums look like in the context of rolling 2 dice? I will continue though. So if I kind of finish up this pyramid, or well, it's not really a pyramid, it's kind of the stack. There's 6 different dice combinations that give me a sample minimum of 1. And there's also going to be dice combinations that give me a sample minimum of 2, but not 2, 1, right? So I'm going to have to start with 2, 2, and then 2, 3, and then 2, 4, 2, 5, and then 2, 6 would be kind of the last one. And then I can think about sample minimums that give me a or combination that give me a sample minimum of 3, and then I'm going to have to start with 3, 1 because I already have, 3, 3, because 3, 1, and 3, 2 are already being used in the other 2 columns. So in order to get a sample minimum of 3, I start with 3, 3, and then there's 3, 4, 3, 5, and 3, 6. And so you can kind of see what happens here, that there's fewer and fewer combinations as I go up. So I'll just kind of cheat a little bit and finish filling this out. That my distribution of possible sample minimums is going to look like this if my sample size that I'm drawing from here is 2, if I'm drawing 2 from this population at a time. Now I could kind of think about what would happen with larger samples, right? So if I think about the distribution of possible sample minimums that I would see with 4 dice at a time, or 7 dice at a time, or 10 dice at a time, you can kind of think about that. Maybe you want to take 30 seconds and think about that first before I keep talking. But there's going to be more and more combinations over here if I have larger sample sizes, and there's fewer and fewer combinations that I'm going to see on this side, right? Because if I take a sample of 10 dice, chances are starting to get high that I'm going to see a 1 in there, or at least a 2. It's going to be really, really hard to get samples of 10 dice that are only like 3, 4s, 5s, and 6s, right? Certainly, it's like the idea of getting 10 6s is going to be pretty impossible. Not completely, but pretty improbable, I should say. Same thing of being all 5s and 6s, that's going to be hard. So the larger the sample I take, the more likely I am to get a sample minimum way over here. And so that's what we're going to see here if I kind of draw this out. So sample minimums from 2 dice rolls, 4 dice rolls, and 10 dice rolls. You can see that my sample minimum distribution is going to kind of converge around the true minimum of this distribution. It's going to begin to kind of converge around 1, because the larger the sample size I take, the harder it is to not get a 1 to make that my sample minimum. Now, this one's a little bit different than means, right? And so you might kind of notice this already, that with means, it's kind of converging symmetrically around the true population mean of 3.5. It's kind of converging from both sides there. Whereas with a parameter like the minimum, I'm only kind of converging from one side. And so this is where these 2 terms come in. I think I've probably mentioned them at least once before, but I'll mention them again here. Some statistics are what we call biased estimators, and some statistics are what we call unbiased estimators. The sample mean is an example of a unbiased statistic, an unbiased estimator, because the distribution is going to be centered around the true parameter. That if I take the mean of all my sample means, it's going to be about 3.5. It's going to center around the true parameter. Whereas over here, if I take kind of the mean of all my minimums, it's not going to be 1. It's going to be some value greater than 1, because I can't get a sample minimum less than 1, and I'm going to have some that are above 1. So the sample minimum is an example of a biased estimator. It's a biased estimate of its parameter. So I mentioned this just because I think it kind of helps us brainstorm a little bit more about what a distribution of a sample statistic is, and how, depending on the sample statistic we look at, it's going to behave a little bit differently. So some are going to be unbiased estimates and symmetrically approach their parameter. Some are going to be biased estimates, and they're going to kind of approach their parameter from one side. The standard deviation is another example of an estimate that can be biased. However, we divide by n-1 to make it unbiased. So I think I have talked about that before in the class. But if I were to divide by n in the standard deviation formula, I'd be more likely to underestimate the true standard deviation of the population because of how the formula works and how it's using a sample mean instead of a population mean in the formula. So that is why statisticians use the n-1 correction in the denominator, because if I do that, standard deviation will now be an unbiased estimator of the true standard deviation. And so we can kind of see that here. So we have a distribution of sample standard deviations if I was using 5 dice rolls versus 10 versus 20, that it is going to begin to converge around the true parameter. And so this is with the n-1 denominator. If I didn't have that, if I just divided by n, my distribution would be slightly heavier. Oh, wait, sorry. I misunderstood what I did with these pictures. There is a tiny red line and a black line in each one. So the red line represents the mean of my biased estimators, the mean of my standard deviations for this group. And you can see it's slightly underestimating the true standard deviation there. However, as I increase my sample size, the bias gets less and less, and I begin to see the mean of my standard deviations kind of converge around the true standard deviation of this population. So sorry, I momentarily forgot what I did with these pictures, but now I remember. Okay, so all that to say, that's why we divide by n-1 is because of this little bias element, that if we divide by n-1, then that little gap will go away, and my standard deviations will kind of distribute symmetrically and centered on the true population standard deviation. Okay. All right, so just kind of a quick recap here. Which of these statistics do you think will be biased estimates of their parameter? Which do you think will be unbiased estimates? So the first one we have is the sample range. The second is the sample median, and the third is the sample maximum. So I'd encourage you to kind of think about this. We covered a lot of stuff in this section. It might feel a little bit confusing and complicated. So this might be a good chance to kind of go back and read a little bit about what we just talked about. And then, think about this question. Which of these do you think might be biased estimates of their parameter? Which do you think might be unbiased estimates, and why? I will go ahead here. So the sample range, if you think about how this works, if I think about it in the context of dice rolls, the true range for dice rolls should be 5, because it should go from 6 to 1. It should be 6 minus 1 would be the true range of dice rolls. Well, if I think about the ranges that I'm going to see from a sample, I might get a 1 and a 2, a 1 and a 1, a 3 and a 4, 3 and a 5, right? So I'm going to see a lot of sample ranges of 1 and 2 and 3, and maybe once in a while I'll get a 5. So my distribution of possible sample ranges is going to underestimate the true population range of 5 pretty consistently. And the larger the sample size I take, the more often I'm going to see sample ranges around the true parameter of 5. So the sample range is going to be a biased estimate that's going to grow a little bit more accurate with larger samples. So if I have a large sample, then chances are I'm going to see a 6 and a 1, and my sample range is going to be correct. But I am very consistently going to underestimate the range with just my sample. So I'll kind of write over here in red. We'll consistently underestimate the true range of 5. So this, by the way, is in the context of dice rolls. Oops. Okay. The sample median, so if I think about dice rolls again, just as an example, the true median should be 3.5. It should be kind of the middle of 3 and 4. So since dice rolls, the distribution is symmetric, The mean and the median should be the same in that case. And so if I think about the sample median, so the median of the dice rolls that I took, I should be consistently estimating around it. I should be just as likely to be below 3.5 as I am to be above 3.5 with my sample median. So the sample median is an example of an unbiased estimate, of an unbiased estimator. So I should be, or I'll say I should be just as likely okay. And then the last one is the sample maximum. And so this one might be a little bit easier to think about because we've already thought about the sample minimum. And we're going to have the same issue with the maximum as we do with the minimum, meaning that this is going to be another biased estimator. Because again, if I think about a sample maximum, the true maximum is 6. And most of the time, my sample maximums may not be 6 because I may not have a 6 in my sample. So I can only underestimate it or get it correct. So sample maximum is going to be a biased estimate for the same reason that a sample minimum is. Okay. All right, so we talked about a lot of stuff, and some of this biased and unbiased estimate stuff is really kind of extra to kind of give a little bit more context because I just think this conversation can help give more depth to what we're talking about. But I will kind of tell you, if you're a little bit fuzzy on this part, don't worry so much about that. I would say the big idea to take from this section is that what we started with at the beginning, that a sample distribution should estimate the population distribution as I have a larger and larger sample. For the same reason, so kind of the picture that goes with that. For the same reason, a sample statistic is trying to estimate a parameter. And the larger the sample I take, the more accurate I expect my sample statistic to be in estimating that parameter. I can also think of my sample statistic as having a distribution of possibilities, that if I take a sample of size whatever, if sample of size n, there's a distribution of possible sample statistics that I could get. If we're talking about a sample mean, it should be distributing symmetrically around the true parameter, and I'm going to get a sample mean somewhere in this distribution that's hopefully pretty close to the parameter, but could be a little bit farther away sometimes. And that also, each sample statistic that I could look at has its own kind of behavior and is going to distribute in its own way. So some sample statistics are going to distribute symmetrically around the parameter they're estimating. Some sample statistics don't do that. They distribute asymmetrically around a parameter. However, all sample statistics are going to converge towards their parameter when the sample size is large enough. The larger the sample size I take, the more that distribution of possible sample statistics is going to converge and approach the parameter it's trying to estimate.